Welcome to The Explainer. Today, we're going to completely demystify the math behind how we arrange the world around us. We use words like combinations literally every single day, right? But mathematically speaking, we're often using them completely wrong. So let's just dive right in and fix that. I want to hook you right off the bat by pointing out a little lie we all accept every single day. Think about a fruit salad for a second. Your fruit salad is just a mix of apples, grapes, and bananas. We really don't care what order the fruits are chopped up in, right? Bananas, grapes, apples, it's all the exact same delicious fruit salad. Now compare that to your standard combination lock on a safe. If the code is 472, the order absolutely matters. 724 is definitely not going to open that safe. So the great lie is this: your combination lock is actually a permutation lock.
So, here's our quick roadmap for today. 1. The combination lock lie. 2. Permutations where position matters. 3. Combinations. 4. The ice cream problem. And 5. The master grid. All right, let's jump straight into section 1, the combination lock lie.
Building on that fruit salad and safe lock analogy, we really need to anchor the exact mathematical difference between our two core concepts. You see, in math, we use very precise language. When the order of the things you're selecting doesn't matter at all, well, that is a combination. But when the order absolutely does matter, it's a permutation. Basically, a permutation is just an ordered combination. So yeah, society has literally been mislabeling locks for decades.
Moving on to section 2, permutations. Position matters.
Now, if you take away just one simple mental model from this whole explainer, please let it be this: permutation equals position. They both start with the letter P, which makes it super easy to remember. Whenever you're faced with a real-world problem and you realize that swapping the position of two items creates a distinctly different outcome, like swapping the numbers on a lock or the runners finishing a race, you are absolutely dealing with a permutation.
Now, within the world of permutations, there are actually two distinct types, and believe me, this fundamentally changes the math. The first type is when repetition is allowed. Think of that lock again. Your code could absolutely be 333, right? The second type is when there is no repetition. Think of the first 3 people crossing the finish line in a sprint. You physically cannot be in both first and second place at the exact same time. Adding or removing the ability to reuse items completely changes our mathematical reality.
So let's look at permutations where repetition is allowed. The math here is just beautifully simple. Say you have a lock with 10 numbers on it, 0 through 9, and you need to choose 3 numbers. Well, you have 10 choices for the first digit. Then, because you can repeat, you still have 10 choices for the second digit and another 10 choices for the third. You just multiply them together. 10 times 10 times 10, which gets you 1,000 possible permutations. It's literally just the number of options to the power of the number of choices you're making.
But let's see how this shifts when we are not allowed to repeat items. Imagine you have a standard set of 16 pool balls. If you draw one ball out of a bag, you have 16 possibilities. But for your second draw, well, that first ball's already gone. Now you only have 15 possibilities, then 14, then 13. Without repetition, our available choices literally shrink every single time we make a selection.
Now, writing out 16 times 15 times 14 all the way down to 1 every single time you do math would be totally exhausting. So mathematicians use a really brilliant shortcut, the factorial function, which is represented by an exclamation point. For example, 4 factorial simply means 4 times 3 times 2 times 1, which gives us 24. It keeps our equations incredibly clean. And, here's a fun math fact for your next trivia night. It's generally agreed in mathematics that 0 factorial actually equals 1. I know it seems super weird that multiplying no numbers together gets us 1, but doing this helps simplify a massive amount of complex equations down the road.
What's really wild here is the sheer scale of factorials. If we wanted to arrange all 16 of those pool balls, 16 factorial gives us over 20 trillion permutations. Mind-blowing, right? But what if we only want to pick 3 balls out of the 16? We obviously don't want to multiply all the way down to 1. We just want 16 times 15 times 14. So the neat mathematical trick here is to divide 16 factorial by 13 factorial. The 13 times 12 times 11 on both the top and the bottom beautifully cancel each other out, shrinking our massive 20 trillion number down to a very manageable 3,360 different ways to arrange 3 balls. All right, let's jump to section 3, combinations. Order doesn't matter. So this is exactly how lotteries work. Think about it. If you hold the winning numbers, it doesn't matter at all what order they were drawn in, right? As long as you have them, you win. To calculate combinations, we actually start by doing exactly what we just did. Step 1, Assume order matters and calculate the permutation. Then, step 2, we alter it mathematically so order doesn't matter anymore. We do this by reducing our total number by all the redundant duplicate layouts. So basically, combinations are just permutations that we've mathematically shrunk to get rid of duplicates. Let's say we picked pool balls 1, 2, and 3. Take a look at the left column here. In a permutation where order matters, 1, 2, 3 is a totally different result from 3, 2, 1. In fact, there are 6 distinct ways to arrange those 3 specific balls. That's just 3 factorial. But in a combination where order doesn't matter, all 6 of those permutations collapse into just one single outcome over on the right, the simple group of balls 1, 2, and 3. So to find our combinations, we literally just take our permutations and divide them by the factorial of our group size. And when we actually do that math, dividing our 3,360 permutations by 6, which again is the number of ways those 3 balls can be redundantly ordered, we get exactly 560. This is known in mathematics as the n-choose-r formula, or the binomial coefficient. It takes the massive, overwhelming possibilities of permutations and beautifully shrinks them down to 560 perfectly manageable combinations. Next up, section 4, the ice cream problem. Okay, to ground what is actually a really tricky abstract concept, let's set the stage with a scenario we can all relate to. You are at an ice cream parlor. There are 5 flavors available: banana, chocolate, lemon, strawberry, and vanilla. You're super hungry, so you want 3 scoops. And importantly, repetitions are allowed here. You could totally get 3 scoops of chocolate if you want. Order doesn't matter because it all goes into the exact same bowl anyway. So how many variations are possible? To solve this one, I want you to imagine you're programming a robot to get your ice cream from 5 flavor bins lined up in a row. The robot only understands 2 simple commands: scoop, which will represent with a circle, and move to the next bin, which will represent with an arrow. So if you want 3 chocolates, the robot moves past banana, scoops 3 times a chocolate, and then moves past the rest of the flavors. This translates our ice cream choices into a literal sequence of arrows and circles. Instead of worrying about flavors, our problem becomes beautifully simple. How many different ways can we arrange 3 circles and 4 arrows? By turning our ice cream scoops and flavor bins into a total of 7 positions, that's 3 scoops plus 4 moves, we just use our standard combination formula to see how many ways we can place our 3 circles into those 7 slots. And the math elegantly works out to exactly 35 variations. Visualizing the problem like this, with a robot moving between boxes, really proves that even the most complex, headache-inducing math formulas become totally intuitive when you just frame them the right way. Bringing it all home now with section 5, the master grid. I want you to take a mental snapshot of this unified cheat sheet right here. This 2x2 matrix organizes everything we've just learned. On the vertical axis, we ask, does order matter? If yes, it's a permutation. If no, it's a combination. On the horizontal axis, we ask, are repeats allowed? Just by answering those 2 super simple real-world questions, you can instantly zero in on the exact mathematical formula you need. This is basically your brand new mental map to decode the arrangements of the universe. As the source material beautifully states, knowing the formulas is really only half the battle. Figuring out how to interpret the real-world situation in front of you, that's where the true challenge lies. So I'm going to leave you with this final provocative thought. Armed with this new matrix, what everyday scenarios have you been calculating wrong your entire life? Next time you set a luggage lock, buy a lottery ticket, or order a triple scoop sundae, you'll know exactly the math going on behind the scenes. Keep questioning, keep learning, and I'll see you in the next explainer.